Hey y'all, my name is Prashanth Kumar, or PK, and I'm an MCAT tutor at Shemmassian Academic Consulting. Today, we're going to be taking on an MCAT Chem Phys passage, and we're going to be going through some tips, some strategies, everything you need to help you tackle this section. You're going to want to take roughly 8 minutes on each of these passages, but today, we're going to be going more in depth so you can see exactly what's going on in my head as I tackle this passage. Let's get it. So I've gone ahead and put the passage on the left and all 5 questions we're going through on the right. Feel free to take a moment to pause the video, answer the questions, and then come back to us. If not, let's get right into it. So here's the passage. But before we get into the passage, let's talk strategy. Having a sort of game plan before you tackle any passage is super important. The reason I say so is because it's important to build routine. Routine builds confidence, and confidence is imperative when you're taking the MCAT. So I want you to have sort of a game plan how you're going to tackle every single passage, no matter whether it's easy, no matter whether it's hard. We don't want to have any hesitation as we see a passage. That's it. So for me, that looks like reading a paragraph, writing a 3 to 5 word summary, going on to the next paragraph, 3 to 5 word summary, and on and on and on. The reason I like to do this is because it provides accountability. After I read a paragraph, the 3 to 5 word summary is nothing crazy, nothing detailed. It's just a quick check-in to make sure I'm understanding what's going on in the passage. That way, I don't spend time getting lost and then just reading empty words, because that's what I was doing a lot. After the end of the passage, I feel myself not understanding anything, and that's really, really tough because you have to reread the entire passage. Here, by doing this little check-in, and make sure you understand the passage, and then you can come back and then reread the paragraph if needed. This helps prevent any wastage of time, and it honestly helps you understand where everything is in the passage. So the second really helpful tip, I think, is to not spend too much time on the figures. The reason for this is we don't really know what details are important, if any. Maybe the passage doesn't even ask about the figures. And if we spend 5 minutes or however many minutes on a passage, that's not going to be super helpful if we're not going to come back to that figure, right? So I like to do like a shallow glance maybe, and then come back to the figure when I need to, because we'll ultimately come back to it if a question asks for it. So with that, let's get right into it. A team of public health experts and engineers are overseeing the construction of a pipeline to bring safe drinking water to a community. The water source contains harmful compounds, and the resulting water must be treated. One of the final stages of water treatment is disinfection, in which a disinfectant such as chloramine is added to kill any microbes surviving previous stages of treatment. So here I like to check in, ask myself, quick question, what's happening? And 3 to 5 words, nothing crazy. I just write disinfect H2O. That's really all I'm writing because it's a simple summary. I don't know what details are important, if any. And by doing this, I just understand we're talking about disinfecting water in this passage. So let's go into the next paragraph. To continuously inject disinfectant to the moving water supply, the team has opted to employ a Venturi siphon, a device that utilizes the Venturi effect and local points of low pressure to draw fluid from a reservoir. In this case, a reservoir filled with disinfectant into a main pipeline. Again, what's happening? So I'm going to say disinfect by Venturi, right? I don't know exactly what the details are important, but in this case, I understand that there's some sort of disinfectant happening using a siphon with the Venturi effect. Great. And again, arrows, abbreviations, perfect. We're trying to be quick. No one else is going to be reading what you're writing down, so it doesn't really matter how quick you are. Next paragraph. The shape of the pipe where the siphon is located is shown in figure 1. At point 1, the radius is 0.5 meters. The absolute pressure is 200,000 pascals, and the linear flow velocity is 0.5 meters per second. The radii at points 3 and 4 are 0.25 and 1 meter respectively. Okay, so again, what's happening? And here, I'm just going to write siphon details. I don't know what details are important. There's like 8 numbers there. I honestly don't know what's going to be asked in the passage, so I can't really focus on it too heavily right now. So that's it. Let's go on to the next thing, and that's the figure. What did we say? Figure. Glance, nothing crazy. I see it's some sort of flowing through a siphon, different radiuses, different stuff, but at the end of the day, not going to spend too much time because we'll probably end up coming back to it. Final thing, the water is assumed to be incompressible and flowing without turbulence. So I'm just going to go ahead and write conditions here. These are, you'll see conditions in nearly everything, any passage you come up with in chemistry and physics or biology, just how the experiments work or just how an idea is based on these conditions, right? And so now we're ready to go into it. We understand the basic idea. We have a siphon, we're disinfecting water, right? And now we can go and answer the first question. So let's go. So first question's right here. Let me put it right over here. At which point in the pipe is the water flowing the fastest? A, point 1, because the flow is closest to the source. B, point 2, because the flow is being constricted gradually. C, point 3, because it has the smallest radius. D, point 4, because the largest radius offers the least resistance. All right, so this is inherently asking us to look at this sort of figure because there's 1, 2, and 3, and 4, and that's the points on the figure. So the question's asking for what? And so I'm not a big fan of highlighting, but if you are, I would just highlight what the question's asking. Flowing the fastest point, right? The fastest speed of flow. And so to do this, we have to understand what's called the Venturi effect. And this is saying a fluid increases in speed and decreases in pressure as you constrict. And so we'll walk through this through a formula I like to think about, and that's that the flow rate is constant. The volumetric flow rate is constant through if it's given that it's incompressible and flowing without turbulence. And so that is based on A, which is area, and V, which is the linear flow rate. Okay, so that's what we think about in terms of speed, right? How fast is this fluid flowing? And so the reason we write it as Q is this is going to be constant. Okay, so if you want, we can just write it as constant equals AV and leave it as that. And so I think this formula is super helpful in understanding the trends, right? If something is constant, that's unchanging. So what happens if we change the variables on the other side, right? So let's take for the first example. What happens if we increase A, right? We increase the area. That means for that constant to stay constant, we're going to have to decrease that linear flow rate, right? And that's the same idea. If something's constant, so let's say we double and scale something, we're going to have to half something else for it to multiply and keep that constant. So the other idea is what happens if A decreases, right? If A decreases, exactly, V must increase. And so if we have this basic understanding, we are able to solve this question pretty easily, right? So we're looking for flowing rate the fastest. So V is the highest. And so what do we want to be true when V is the highest? We want area to be the smallest, right? And so we're looking for an answer choice with the smallest area. And the area is referring to area of a cross section. So basically when I draw a line through there, right, we have a slice of each of these sort of areas. And we have a circle in this case, and we have a circle in this case, a circle in this case, and I believe an ellipse in this case might be a circle. I think it's a circle. Yeah, it's a circle. It's just a smaller circle we don't know the exact radius of. So this is the exact sort of thinking that's going on in my head. So now we're looking for the smallest area. And it's pretty clear where it is. If we look at point 3, right, it's a cylinder with a really, really small area of a cross section. And so we automatically can go to point 3, right? And let's look at the justification even. Because it has the smallest radius. And this is a great justification. Smallest radius, if we have a circle, area is what? Pi r squared. And so if we decrease that radius, we're decreasing the area. So that's why C is the answer. If we look at the other answers even, 0.1, because flow is closest to the source, since it's incompressible and flowing without turbulence, it's not really affected by whether it's closest to the source or not. So we can eliminate that. 0.2, because the flow is constricted gradually. We just said flow matters only on the cross-sectional area through which it flows. So if it's more constricted, it'll flow faster. So we can get that. 0.4, because largest radius offers the least resistance. This is not true. We just said smallest area and smallest radius means that we have the flowing the fastest. So right away, 1 for 1, easy question, let's go. And we can go on to question number 2. So in the diagram above, the siphon itself is not shown. At which point should the siphon be placed if it is to draw disinfectant from the reservoir? Okay, so right now, I don't know exactly, it's just asking for the location, but let's go ahead and read the choices. 0.1, the flow has not yet been disturbed. 0.2, because it has the lowest pressure. C, 0.3, because it has the lowest pressure. D, 0.4, because it has the most free space. All right, so right away we see it's a similar type of 2x2 question, right? It's asking for a location and a justification. And we see that these two sort of have a similar justification. So that's something to remember in terms of eliminating answer choices, right? So let's read more about the siphon. I don't really remember where the siphon should be placed. It doesn't really say exactly where it should. So let's go back to the passage, right? And so if we look right here, it should say a Venturi siphon, a device that utilizes the Venturi effect and local points of low pressure to draw fluid from a reservoir. So if I were to highlight something, which I'm not really a big fan of, but I'm just showing you where I'm looking right now, local points of low pressure to draw fluid from a reservoir. All right, so this is another important detail, right? We see low pressure and we want that. That's where we want the siphon to be, right? And so automatically we can eliminate A and D. We're trying to eliminate choices. If we can get rid of 2 choices, now we're already down to a 50-50, and that's amazing, okay? So now we're determining between 0.2 and 0.3. And so let's take a look at 0.2 and 0.3. Well, we said 0.3 was flowing the fastest, and that means it's flowing faster than 0.2. But we need to remember how flow rate and sort of cross-sectional area is related to pressure. And so what we should actually know is with fluid pressure, when it's flowing through a sort of space, it is also affected by what we said earlier, the Venturi effect. Whereas if it's flowing faster, it's going to have lower pressure. Whereas if it's flowing slower, it's going to have greater pressure. And this is oftentimes a little counterintuitive because people will often say, oh, if it's flowing faster, it must be high pressure system. But if we think about it, when it's flowing so fast, it doesn't have time to flow against sort of the walls of the barrier. And so if we're trying to think about its ability to push out and create more pressure on the walls, it's impossible since every single molecule is moving so fast. So this is a part of the Venturi effect, saying that if it's moving faster, we expect it to have the lowest pressure. And so our answer choice, again, is 0.3 because it has the lowest pressure. So this is also due to the Venturi effect. Feel free to go give it a read. Very important idea in fluid mechanics. But let's go on to question 3. We're 2 for 2. Come on. Dun, dun, dun. Let's see. Question 3. Okay. So here we have a question. What is the linear flow velocity of the water at 0.4? So we have 0.1 meters per second, 0.125 meters per second, 0.25 meters per second, and 0.75 meters per second. So we are going to have to do calculations here, and that's an inevitable part. So the idea is we need to understand what the calculation is going to be, right? And so the idea is we need to figure out flow velocity, which is that same V we were looking for, right? And so we need to take knowns and unknowns and put them together. And so there's an equation that's very helpful, which is called the flow rate equation, right? It's the continuity equation. It's saying that since the flow rates are are going to be constant throughout the system, right? That means we can set them equal to each other based on the area of the first and the speed of the first and the area of the second and the speed of the second cross section. So I'll write the equation right there. A1V1 equals A2V2. And if we're thinking about this, it's a cross-sectional area of the first space times the speed at the first place equals the cross-sectional area at the second space and the velocity, or the linear flow velocity at the second space. And so right away, we're trying to see what details do we know that can help us find this, right? And where do we go? Paragraph 3. It gives us details with flow velocity, right? It tells us at point 1, the radius is 0.5, and the linear flow velocity is 0.5 meters per second. And we know that at point 4, which is where we're looking, right? It says points 3 and 4. The radiuses are 0.25 and 1. And so let's say that instead of A2 and V2, I'll go ahead and write A4 and V4 because that's what we're looking for, right? And the question is asking us for V4. So let's plug in what we know and see what we're looking for. Okay, so area of a cross section at point 1 is going to be a circle, right? And what's the area of a circle? Pi r squared. Yes? And so in this case, we know r is 0.5. That's what it says right there. So when we write it out, we're going to write pi times 0.5 squared. And then what is the velocity at this first point? The linear flow velocity is 0.5 meters per second. So I'm going to go ahead and write 0.5 again. And I'm going to say that's equal to the area of cross-section of 4. Same thing. Pi times what's the radius at point 4? Well, we see right here, the radius is 1 meter. So we're going to put pi times 1 squared times V4. And again, V4 is what we're looking for, so we're going to go solve for that. And you have to be very comfortable with calculations, but they're never going to be too challenging. The MCAT, notorious for giving you math that's easy to do if you're able to sort of think about it in some special way, or not to focus too much on the numbers, but rather like approximate and solve from there. So right away we see pi, right? 3.14. I hate multiplying by pi without a calculator, but we see that it's on both sides. So we can just cancel it out, right? If it's on one side and the other, we're just dividing both sides by pi and getting rid of it, right? And so now we have 0.5 squared. And so starting from left to right, 0.5 squared, what's that? Well, 0.5 is 1/2. And what's 1/2 times 1/2? It's 1/4, right? And then we multiply it again by this 0.5. So 1/4 times 1/2, that's equal to 1/8, right? Great. And so right away, we know that this is equal to 1 squared, which is 1, right? So we can get rid of 1 squared. And that's just equal to V4. Okay, perfect. We're at a point where we've solved the equation. Now the basic idea is to understand what is 1/8. If you can understand that 1/4 is 0.25, right? You're just halving 1/4. So what is 0.25 divided by 2? It's 0.125, right? And so right away, we solve that. Not too hard, just a requirement of understanding a formula of flow rates being constant and plugging and chugging. And again, the calculations aren't too crazy, but there are tips and tricks to help you get there, right? We can eliminate pi. We're not multiplying by 3.1415. We're going to multiply by just 1/2 times 1/2 times 1/2. And if we can do that, all the math we need for that question. Let's go. 3 for 3, crushing it. Imagine the tube in the image becomes clogged at point 4. Assuming a required force of 100 newtons to unclog it, what is the minimum force required at point 1? 25 newtons, 50 newtons, 75 newtons, 100 newtons. All right, so we have this force of 100 newtons. If we're highlighting 100 newtons at point 4, right? and it's asking the minimum force required at point 1. And so this is a very, very tough question, right? It's asking us how we have this one force on one side, what's the force required at this other side? And it uses this idea called Pascal's law. Pascal's law is a little different because it's saying that we take a pressure and we apply it to a fluid, right? And what happens when that fluid is incompressible? That is the important condition, incompressible, right? The fluid's applied force is going to be equal at every single part of the fluid. So the idea is, let's say we had, this is just an external drawing I'm saying, is if we have this like tube, right? If we apply this sort of pressure on one side, that same pressure is going to be exerted on the other side. So that's the same idea. Since the fluid has a pressure, applied pressure added to it, it's going to be the same regardless of where you are in the fluid. So with this piece of information, another formula comes up. We're crushing the formulas right now. But it's the idea of what is pressure, right? Pressure is force over area, right? So if we understand that pressure is force over area, then, and we understood Pascal's law, we have two pieces of information that tie together perfectly to help us solve this equation. So we're going to say this force exerted at point 1 over force exerted, or sorry, not force, area of point 1 is going to be equal to the force at point 4 over the area at point 4. So this is a challenging concept, so let's go over it again, right? We're saying, first, pressure is equal to force over area. That is the formula of pressure. The second part that helps you tie it together is Pascal's law. When we're applying pressure to a fluid system that's not incompressible, the pressure applied will be the same at every single point of the fluid. So that's why I'm saying this sort of pressure at point 1 will be equal to pressure at point 4. And note, this is not the same as fluid pressure. This is applied pressure. This is the pressure we're applying. Fluid pressure, like we said in question 2, changes based on where you are in the constriction zone, what the radius is. So with this, it's a simple plug and chug. Force at point 1 is what we're looking for, right? Because that is what we highlighted here. Area at point 1, well, this was the pi r squared, pi times radius at point 1, 0.5 squared, F1 equals F4, and this is where we said 100 newtons, and area at 4 is pi times 1 squared. The same exact math that we've done before, and what do we say? Let's try to simplify it as much as we can. If we get rid of the pi's by multiplying both sides by pi, and what else? We said that this was, I'm going to draw it here so we have more space. This is F1 over 1/2 squared, which is 1/4, equals 100 over 1 squared, which is just 1. Great. So now, what do? Well, let's do our math. We multiply both sides by 1/4, okay? So that cancels here, and then 1/4 times 100 is 25 newtons. So if we have 100 times 1/4, we get 25 newtons, and let's see, A is 25 newtons, and we've done it. Great work, team. Absolutely crushed that, so congratulations. Fluid mechanics, an absolute beast of a topic on the exam, but very, very important nevertheless. We covered Pascal's law. We talked about flow rates and pressure with the Venturi effect. We discussed the continuity equation. So much content, and we did it. We reviewed it, and we absolutely destroyed that passage. Congratulations, and hopefully that review was helpful. Hopefully seeing those strategies and those tips and tricks helped get you in a state where you can apply some of these things to your passages in your MCAT. If you enjoyed this video, please give us a like and subscribe below. Sign up for our MCAT question of the day so you don't miss out on any practice before test day. And also check out our 528 series for even more tips, strategies, and helpful guidance as you dream to score your 528. Let's go, congratulations, and I'll see you next time.